Acid strength. You learned about strong and weak acids in Chem 1A in a very general way. The strength of an acid, the strength of an electrolyte, depends on how far does the dissociation happen. And so now we know a lot more about equilibria, right? And we know that you can have an equilibrium that's like half and half, or one that's almost entirely to the products, or one that hardly goes to the products at all. So a strong electrolyte will dissociate completely. It will make lots and lots of ions. A weak electrolyte only dissociates partially. So the strength of an acid has nothing to do with its concentration or how dangerous it is. It depends on the equilibrium. So here's our acid, and we'll see this often used as a representation for a generic acid. So there's the hydrogen ion, and this would be an A- ion, which is not an element on the periodic table. So here's our generic acid. It can donate a hydrogen to a water molecule, forming hydronium ion and this conjugate base, A-. So if we have a strong acid, this reaction is going essentially to completion. If we have a weak acid, the equilibrium is going to lie mostly to the left. Oh, I don't think we have any pictures of conduction apparatuses. I'm going to draw one. It'll be ugly. So here's a beaker of liquid. That's my attempt at a light bulb. And that's a battery. And here are electrodes, pieces of metal stuck in the liquid. And we'll connect these guys up to the battery. So the battery has enough power to light up the light bulb. But our circuit is not quite complete there. Let's get that right. If we stick these two electrodes in pure water, water does not conduct electricity. Pure water does not conduct electricity. Does that seem to contradict something you've learned? Yeah, well, what about the whole lightning and electricity thing, and you're not supposed to stand on puddles of water when you're doing things like that? Is the puddle of water you're standing in pure water? No. It's got stuff dissolved in it. That will conduct electricity, but pure water won't. If we touched these electrodes together, that would complete the circuit and the light bulb would go on. So if we put a strong acid in this beaker, the light bulb will glow strongly. The light will be strong because there are lots of ions to carry that electric current around. If we have a weak acid, the light bulb will light up a little bit, but the light is weak because there's not very many ions to carry the electricity. So that might help you remember the difference between a strong acid and a weak acid. Strong acid comes completely apart into ions. Weak acids just make a few ions. So there are 6 important strong acids, and you should memorize them. There's only 6 of them. It's not that bad. So here we have hydrochloric, hydrobromic, and hydroiodic acid. What do these 3 have in common? Well, they're all binary acids, but they're all involve the halogens, right? So we got chlorine, bromine, and iodine with hydrogen. The lower ones, the bigger ones, are strong acids. What about HF? HF is not a strong acid, therefore it is a weak acid. The way I think of that is fluorine is like the little sister of that family, and she's not very strong. So HF is a weak acid, the other three are strong. So a little something to help you with those. And these guys, I got nothing. They're familiar. Nitric acid, perchloric acid, and sulfuric acid are also strong acids. Diprotic means it has 2 protons that it can ionize or donate. So these other acids would be called monoprotic or 1-proton acids. You can also have a triprotic acid. Can anybody think of a triprotic acid? H3PO4. Yeah. Phosphoric acid, phosphorus acid, 3 protons that can be ionized. If we were able to look at a solution of hydrochloric acid and examine the individual particles, what we would find is that there are virtually no intact molecules. In Chem 1B, we don't say that there are no, or that the reaction goes to completion. We say it goes almost entirely to completion, because now we know that that equilibrium constant might be really, really small or really, really big, but there still might be a couple of ions that form. So virtually none. So here we have the hydrogen and the chlorine, and they form ions. The hydrogen goes and hangs out on the water molecules, right, and piggyback or something, and then here's the chloride ions. We're not going to see any of these guys in solution because it's a strong acid, comes apart, makes lots of ions. The light bulb has a strong light. So when we draw the reaction or the equation for this, we're going to use a single arrow, meaning this only goes in one direction. So if we have a 1.0 molar HCl solution, then we know that the concentration of H3O ions, H3O plus ions, hydronium ions, would also be 1.0 molar. And what would the concentration of chloride ions be? Also 1 molar. Because 1 mole of HCl makes 1 mole of hydrogen ions and 1 mole of chloride ions. Here's the little sister, fluorine. So HF, hydrofluoric acid, is a weak acid. So when this dissolves in water, we get a few fluoride ions and a few hydronium ions, but mostly what we see are the intact HF molecules. This is a weak acid. Would the solution conduct electricity? Yes, but not very well. So here we're going to put the equilibrium arrow showing that this reaction goes in both directions. And in fact, most of the time it's over on the left side. So if we have a 1 molar solution of HF, we can't immediately tell what the hydronium ion concentration would be, because some of these are going to ionize, but most of them are not. And how do you know how many? For now, all we can say is that the hydronium ion concentration is going to be a lot less than 1 molar, because only a few of these ions will form. Any questions? Yes?
So, in that case, can we use the ice table?
We will be using ice tables, yes, and equilibrium constants. Yep, exactly. Any other questions? So the strength of an acid depends on the attraction between the hydrogen ion and that anion, the conjugate base. And this is kind of counterintuitive, but the stronger the acid, the weaker the conjugate base. So if we look, not like that. If we look at a strong acid, there's a very weak attraction between the hydrogen ion and the conjugate base, the anion. So that when this is in an aqueous solution, the attraction is weak, and so it comes apart into ions. It's a strong acid. Whereas with a weak acid, there's a strong attraction between the hydrogen and the anion, and so it only ionizes partially. And this is why I like to think about the strong light from the light bulb and the weak light from the light bulb, because this bothers me that we have a weak attraction on the strong acid and a strong attraction for the weak acid. So think of the light bulb when you're identifying these. Come on. There we go. So we have an equilibrium constant for the ionization of a weak acid. And this is called the acid ionization constant, and it's K with a subscript A. And this is a way of quantifying how strong or how weak an acid is, the strength of an acid. So we're going to look at the acid plus water, which is what happens when you dissolve it in water, and that's going to form hydronium ions and the conjugate base, the anion that's left after the proton is donated. So this gets kind of messy, right, because it's got water in it, and this is why we often just say, well, let's just look at the hydrogen ion, because it ends up being much simpler to look at. So this guy comes apart into a hydrogen ion and an anion. Is this proton swimming around by himself? No, it's actually doing this. But we don't need to put all the water molecules in all of our equations. So Ka for the first one would be the hydronium ion concentration times the anion concentration divided by the acid concentration. In terms of the second equation, the only difference is that we're saying H plus instead of H3O plus. But it's all going to be exactly the same thing. This is just kind of like a nickname for hydronium. So if we have a smaller Ka, that means that the reaction is not going to go to the products very much, right? A smaller Ka means you have a weaker acid, less ionization. So here's a table of acid ionization constants for some monoprotic acids. You don't memorize acid ionization constants. Okay? You'll need them in homework or on an exam. You'll either be given it or you'll have a place where you can look it up, and this is a useful place to look it up. If you want the answers in Mastering Chemistry to come out the same as the correct answer in Mastering Chemistry, I would advise you to use the Kas from this table in the book rather than finding them on the internet. Because there are some differences. This is at 25 degrees Celsius. The other ones might be at a different temperature. They only have two significant figures, so it's not like they're super precise. So if you want the best results, just use these. So a bunch of different acids. Some we've heard of, some not. This shows both forms of the ionization. I'm sorry, it doesn't. It just shows the one. This shows the ionization equation where it's reacting with water and water is taking the proton. In this column, we see the acidic hydrogen, or the proton, in red, and that's the one that's going to be lost. Some of these have more than one hydrogen, but like in benzoic acid, it's only this one that's going to be donated. The rest of them aren't going anywhere. Consider the three generic weak acids, HA, HB, and HC. How creative. The images shown represent the ionization of each acid at room temperature. Which acid has the largest Ka? Does a large Ka mean more ionization or less? More ionization. So we're looking to see which of these has the most ions. Well, the ones that are easiest to spot are the hydrogen ions. This has 1, this has 4, and this one has 2. So which one has the highest? Yeah, HB. Would this be considered a strong acid? No, because it's still mostly the intact molecules. It's just that it has more ions than the other two. Ha, yeah. Well, I actually deal a lot with Ha. So consider these two acids and their Ka values. So you have HF, here's the Ka, and we have HClO, here's the Ka. Which acid is stronger? A is stronger. Scientific notation can mess you up sometimes because here, these are negative exponents. And so with the negative exponents, the smaller the number, the bigger the whole thing is. This has a larger negative exponent, and so this is a smaller number. Any questions?